Today we're talking about the effects of force on velocity, and then we'll dig into Newton's second law of motion and talk a little bit about circular motion too. To start with, we're doing a little short lab that shouldn't take more than about 5 minutes. Okay? What you're going to do is you're going to take one of the clear plastic bins that's up on my desk there, and you're going to attach a piece of string to it using some masking tape. You're going to go find a spot in the room where you can find about a 2-meter stretch of floor, and you're going to pull the box across that stretch of floor, trying to cause it to accelerate. Now, in this case, we mean speed up by accelerate, okay? Then you're going to put an object in the box to add weight to it, take the box back to where you were, pull it back across the floor, trying to make it accelerate as much as you did the first time, and then you're going to come back to your desk and try to answer the question, what do you notice about the force required to accelerate the box with the two different masses? You're going to do this with a partner. There's boxes up here. There's string up here. I'll put the tape up here. Let's get going. So, what did you notice about the force required to accelerate the box with the two different masses?
It needs more when it's more, more mass.
When there's more mass, it needs more force. Good. Okay, so we're going to dig into that a little bit more today. But first, we're going to talk about some stuff that we partially covered yesterday, okay, which is that unbalanced forces affect motion. So objects that are at rest, we learned, only begin to move if an unbalanced force acts on them, and they move in the direction of that unbalanced force. Objects that are already moving can experience changes in their velocity due to unbalanced forces, and we're going to go over what some of those changes are. So, some changes in velocity that an object can experience are, it can begin to speed up. So if the net force on an object is moving in the same direction as that object is moving, then the object will speed up. A good example of this is if you are pushing a friend on a swing, and you give them a push in the direction that they are already moving, they will begin to move faster, right? Their velocity will increase. They're going to speed up. Second change is that they can slow down. If you apply a net force in the opposite direction to the direction that the object is moving, then that object is going to slow down. The velocity will decrease. Good example of this is if you are riding a scooter or a skateboard and you put your foot down on the pavement and allow it to drag, you exert a force in the opposite direction to your motion, and as a result, your velocity decreases. You slow down. And finally, as some of you may have guessed, if you're thinking back to changes in velocity from the previous chapter, that you can change direction with an unbalanced force. So if the unbalanced force is a force in a new direction, it can change the direction of movement of the object. A good example of this is if you've ever played pool and you have a ball hit the railing on the pool table, then the pool table railing is going to exert a force in another direction on that pool ball, and it's going to ricochet off in another direction. Okay? As you might have noticed, what we just described is acceleration from the previous chapter, speeding up, slowing down, changing direction. Now we know that the acceleration of an object is connected to the force applied to that object. Unbalanced forces are what cause changes in velocity. Newton's second law of motion shows us the relationship between force and acceleration. So Newton's second law says the acceleration of an object is equal to the net force acting on that object divided by that object's mass. Or you could phrase it another way. You could say it's the net force on an object is equal to the mass of that object times the acceleration of that object. Okay, the formulas for this would look something like this. It's the same equation, just written differently. Net force is equal to mass times acceleration, F equals m times a, or acceleration is equal to net force divided by mass. A is equal to F over m. You can use these equations to solve for acceleration and net force. So I want you to pay attention to the fact that when you either increase the mass or want to increase the acceleration at which an object is traveling, you're going to have to increase the force. Now we're going to talk a little bit about circular motion, but before we do, we're going to do another little activity, okay? So you're going to need a sock for this one, so if you're not wearing socks, you're going to need a partner who is. You're going to take off one of your socks and roll it up. Then you're going to take a piece of string from the activity we did before and attach it to the rolled up sock, and then you're going to swing that sock above your head in a circular motion so that you do not hit anybody. And then I want you to think about the forces acting on the string and on the sock and write them down. You have 5 minutes again. So, what forces did you feel when you were spinning the sock?
It went around the string.
Gravity. Okay, inertia, you may have felt the response of inertia. Inertia isn't actually a force, but you may have felt it at play. Okay, so let's dig into what that actually looks like. When we have circular motion, you have an object traveling in a straight path, because remember, an object's inertia resists changes to its motion, and changing direction is a change to its motion. Okay, moves in a straight line, resists changing direction. So in order for it to move in a circle, you have to have a force. And the name of that force is centripetal force. Centripetal force is a force that it acts perpendicular to the direction of motion towards the center of the curve. So when you spun the sock, the centripetal force was caused by the string attached to the sock towards the center. Now, some of you said that you felt like the sock was pulling out. And what you were feeling was not actually a force, but it was, in fact, inertia trying to keep that object going in the same line. So the object was resisting a change to its motion, and it required the centripetal force to pull it along that curved path. So the only force in that situation is centripetal force towards the center of the circle that you created with the sock.